Well, hello there. Today we're going to talk about normally distributed data. Now, not all data is normally distributed. If you think about it for a moment, you might measure the average temperature for each month over the course of 3 years. What would that graph look like? What would that data distribution look like? Well, if you started in January, it would be low and it would get warm, and then it would low again, and it would get warm and low and warm, right? It would go up and down. If you were to graph, say, my career scoring in high school, it would be a pretty constant graph. No, I didn't average 28 a game. My points were more like 1, 0, 0, 0, 0, 0, 0, 2. I got lucky and made a layup. 0, 0, 0. You get the point, right? A flat level of data. What we're going to talk about for the next week, and then what you're going to talk about really in your introductory statistics course that you'll take at some point in life, is what we call normally distributed data. Now, that is a loaded word. And you need to know that when we use that word, we're assuming we have data that is normally distributed. As we talked about earlier, normal distribution means we have a little bit down here, a whole lot around the middle, and a little bit out here. And it is perfectly symmetric around the mean. Now, are there data that are really perfectly symmetrical around a mean? Well, it's what we call standardization, and we use it to estimate things, like SAT scores. Are they perfectly symmetrical? No, but they're pretty close. How about the amount of soda in bottles that are 12 ounces? Is it always exactly 12? No, but it's probably a little bit on either side, centered around 12, right? This is called normally distributed data. And what's cool about it is that it doesn't matter whether you're talking about Russell Wilson's touchdown passes, SAT scores, or the amount of soda in bottles, because those values themselves don't really matter. What we're interested in is the number of standard deviations you are away from the mean, because regardless of the data, the percentage is the same. For example, if I go 1 here, 2, 3, 1, 2, 3. That's 3 standard deviations on either side of the mean. What does that mean? That means it doesn't matter if you're talking about SAT scores or Russell Wilson's touchdown passes. You know why? Because this is always going to be 34% of the data. Really? Yes. If the SAT has a mean of 1,000 and a standard deviation of 100, that means there are 34% of the scores between 1,000 and 1,100. Oh, if Russell Wilson averages 2 touchdown passes with a standard deviation of 1, that means 34% of his games are between 2 and 3. The same 34%. That's the beauty of the normal distribution. Now, how do we convert from SAT scores to touchdown passes? Funny you should ask. This is the score formula. Your data point minus the mean divided by the standard deviation. That gives you a z-score. So think about it. The mean itself will have a z-score of, that's right, 0. So really, the mean here, this is 0, and that represents the mean. And then we go up 1, down 1, up 2, down 2. Those are standard deviations. And I could fill in the rest of these regions because we know the percentage of area. So this would be another 34% here because it's symmetric, right? Now this follows the 68, 95, 99 rule. Oh, 68% of the data is within 1 standard deviation. 95 is within 2. Oh, so 95 minus 68 would be 27. So this would be another 13.5%. And then 99% of the data is within 3. So basically, what we have here is about 1.5%, right? Because this is 95, so you'd have 2.5 on 5% left over, 2.5 on either side. So we'll say this is going to be about, I don't know, about 2. Let's see, that's 47.5. So let's make this about 2.5-ish percent. We'll say 2.4%. And 2.4%. It's really close. So you're within 3 standard deviations. That's 99% of the data. That means what? 99% of the kids score between 700 and 1300. Yeah, that's true. So this is how standard deviation and normal distribution work. Now, what we can do is we can use our calculator to calculate both the area underneath and the z-score from the area. Because think about it. If you know the area, you should be able to go back and get the z-score, shouldn't you? Yeah. We're going to have the calculator show us how to do it. And let's see how this works with a problem. Let's say we're dealing with potato chips. And let's say we're told that potato chip weight is normally distributed. As soon as you hear that, you know you're dealing with this situation. We're going to give you a mean. We're going to give you a mean of 9.12 and a standard deviation of 0.05. Now look, I am sure that the potato chip bag probably says 9 ounces. But we magically know in a factory that this is the average weight with a standard deviation of 0.05. So what does that mean? Well, let's draw a normal curve. Now, for the next week or so, you are going to have to get really good at drawing these normal curves. So we're going to draw the normal curve. We're going to put our mean here. We know that's 0, and that corresponds to 9.12. 1, 2, 3. So if our standard deviation is 0.05, why don't you fill in those 3 values? That's right. 9.17, 9.22, 9.27. How about going down? That's right. 9.07, 9.02, 8.97. Now, we ask all kinds of questions because, as you could probably guess, there are more places to be than just 1, 2, or 3. What if you were 1.5 standard deviations above the mean? Can we figure out a percentage for that? Yes, we can. But this is the big idea here. And we're going to use that formula and our calculator to help us work this out. Now, in the next video, we'll work through some problems that use these values with our bags of potato chips. All right, carry on and go normal.